Hello students, welcome again. Today we will learn logarithmic differentiation. So let us see the first example. X raised to 5 into tan cube of 4x divided by sine square of 3x. We have to differentiate this by using logarithmic differentiation. In the last lecture, we have seen two simple examples on logarithmic differentiation. So, here we will solve this example. Let this expression as y is equal to x raised to 5 into tan cube of 4x divided by sine square of 3x. Now, taking log on both sides, we get log y is equal to log of totally x raised to 5 into tan cube of 4x divided by sine square of 3x. By using laws of logarithm, we can simplify this by using law of product, quotient and exponent. We can write log of x raised to 5 into tan cube of 4x minus log of sine square of 3x. We have used here law of quotient of logarithm, which is equal to log of x raised to 5 log of x raised to 5 plus log of tan cube of 4x minus log of sine square of 3x. And by using law of exponent, here we have used a law of product. Here x raised to 5 and tan cube are expressed in terms of product, therefore we used here law of product. And by finally law of exponent, 5 into 5 is exponent, 3 is exponent and similarly 2 is exponent here. 5 into log x plus 3 into log of tan 4x minus 2 into log of sine 3x. This is the simplified form of log y. You can write directly after taking log on both sides directly this step. Now we will differentiate this term with respect to x. So differentiating with respect to x, we can write derivative of log y. Since log y is a composite function, since y is a function of x, log y becomes composite function of x. Therefore, derivative of log y is 1 upon y dy by dx, which is equal to 5 as it is. Derivative of log x is 1 upon x plus 3 into, now observe here, we have to find log of tan of 4x. This is again composite function. Therefore, log of tan is 1 upon, derivative of log of tan is 1 upon tan 4x into, we have to use the chain rule here, into d by dx of tan of 4x minus 2 into derivative of log of sine. Similarly, derivative of log of sine is 1 upon sine 3x into d by dx of sine 3x. Therefore, 1 upon y into dy by dx is equal to 5 upon x plus 3 divided by tan 4x into derivative of tan 4x is derivative of tan is sec square of 4x. It is again a composite function. Therefore, here multiply by derivative of 4x, d by dx of 4x. 3 by tan 4x as it is, derivative of tan is sec square of 4x into d by dx of 4x minus 2 divided by sin 3x into derivative of sin x is cos x. Here derivative of sin 3x is cos 3x into d by dx of 3x. Therefore, 1 by y into dy by dx is equal to 5 upon x plus 3 sec square of 4x divided by tan 4x into derivative of 4x is 4 minus 2 divided by sin 3x into cos 3x into derivative of 3x is 3. Therefore, dy by dx is equal to y into 5 upon x plus 4 into 3 is 12 sec square of 4x divided by tan 4x minus 2 into 3 is 6 divided by sin 3x into cos 3x, which is equal to, replacing y here, x raised to 5 into tan cube of 4x divided by sin square of 3x into bracket 5 upon x plus 12 into sec square of 4x is equal to 1 upon cos square of 4x, and 1 upon tan is cot, and we know that cot is cos 4x upon sin 4x, minus 6 into cos upon sin is cot of 3x, which is equal to x raised to 5 into tan cube of 4x divided by sin square of 3x into bracket 5 upon x plus 12 into cancelling cos 12 divided by cos 4x into sin 4x minus 6 into cot 3x, which is equal to x raised to 5 into tan cube of 4x divided by sin square of 3x into bracket 5 divided by x, multiplying to the numerator and denominator by 2. Here the term will be 2 sin 4x into cos 4x. By using multiple angle formula, 2 sin theta cos theta is 2 sin theta into cos theta is sin 2 theta. Hence, 2 into sin 4x into cos 4x is sin 8x, and multiplying this 12 by 2, it becomes 24 divided by sin 8x minus 6 into cot 3x, and finally the answer is x raised to 5 into tan cube of 4x divided by sin square of 3x into 5 upon x plus 24 into 1 upon sin is cosec of 8x minus 6 into cot of 3x. This is the final answer. The next example is differentiate x raised to tan inverse of x with respect to x. The solution is, let y is equal to x raised to tan inverse of x. Here function is expressed as some function raised to function Therefore we have to use here logarithmic differentiation, and we know that the first step of logarithmic differentiation is taking log on both sides. Therefore, taking log on both sides, log y is equal to log of x raised to tan inverse of x. Now we have to use here laws of logarithm, that is law of exponent, and here tan inverse of x is the exponent. Therefore, by law of exponent of logarithm, tan inverse of x into log of x, that is log x. After taking logarithms on both sides, the next step is to differentiate. Differentiating with respect to x, we get, now remember that derivative of log y is 1 upon y into dy by dx. 1 upon y into dy by dx is equal to, here consider product of two terms. First term is tan inverse of x and second term is log x. Therefore, rules of differentiation, we have to use here rules of differentiation, law of or rule of product or law of product, u into v rule or first and second rule. Substitute first function as it is, tan inverse as it is, into d by dx of log x plus log x as it is into d by dx of tan inverse x is equal to tan inverse x into derivative of log x is 1 by x plus log x into derivative of tan inverse of x is 1 upon 1 plus x square. Simplifying further, tan inverse of x divided by x plus log x divided by 1 plus x square. Now the final step is shifting of y. Dy by dx is equal to y into bracket tan inverse of x divided by x plus log x divided by 1 plus x square, and suppose this y is equal to x raised to tan inverse of x. This is equation 1, and by equation 1 substitute this y is equal to x raised to tan inverse of x. The final answer is x raised to tan inverse of x into bracket tan inverse of x upon x plus log x divided by 1 plus x square. This is the simple example of logarithmic differentiation. This question is asked for 2 marks for our board exam. The next example is sin x raised to x. Let y is equal to sin x raised to x. Taking log on both sides, log y equal to log of sin x raised to x. By using law of exponent, we can write here log of x into log of sin x. Log y is equal to x into log of sin x. Differentiating with respect to x, we get 1 by y into dy by dx is equal to, differentiation by using uv rule, x as it is, derivative of log of sin x, this is composite function, log of sin x is 1 upon sin x into d by dx of sin x plus log of sin x into d by dx of x which is equal to 1 by y into dy by dx is equal to x into derivative of sin x is cos x divided by sin x plus log of sin x into derivative of x with respect to x is 1. Therefore, dy by dx is equal to y into bracket x into sin upon cos is cot x into log of sin x Therefore, by equation 1, replacing y is equal to sin x raised to x, dy by dx is sin x raised to x into bracket x into cot x plus log of sin x. This is the answer. The next example is x raised to sin x. We have to differentiate. The last example is sin x raised to x, and this example is x raised to sin x. So let us solve. Let y is equal to, taking log on both sides, we can directly write the step of logarithm. Log y is equal to now sin x into log x. Since sin x is the exponent, by law of exponent, sin x into log of x. Okay. Differentiating with respect to x, 1 by y into dy by dx is equal to, using UV rule, sin x as it is, d by dx of derivative of log x is 1 by x plus log x as it is, derivative of sin x is cos x, which is equal to sin x upon x plus log x into cos x, and therefore dy by dx is equal to, shifting of this y is equal to x raised to sin x into bracket sin x upon x plus log x into cos x. This is the answer. See the next example. Differentiate e raised to tan x plus log of x raised to tan x. In this example, here addition of two functions which are expressed as some function raised to function. If you observe previous examples, there are single examples or single functions which are expressed as function raised to function, x raised to tan inverse of x, or the next example, suppose sin x raised to x. In this example, here the function is expressed as summation of two functions which are expressed in form of function raised to function. In this type of examples, we have to separately differentiate these two factors, because according to the steps of logarithmic differentiation, we cannot consider here taking log on both sides, since suppose this factor is considered as m and second factor is considered as n. This y will be expressed as summation of two functions, and if we take logarithm on both sides, this term will be log y is equal to log of mn, and which is not equal to log m plus log n. Therefore, we have to differentiate these two terms separately. So, let us see solution of these types of examples. Firstly, we have to consider given example as y. Y is equal to e raised to tan x plus log x raised to tan x. Let u is equal to e raised to tan x. V is equal to second factor log x raised to tan x. Now this y becomes u plus v. Therefore, dy by dx is equal to derivatives of two functions which are expressed in the form of summation. Therefore, dy by dx is equal to du by dx plus dv by dx. Here, the rule of differentiation for summation. Consider this equation as equation 1. Now, consider. Firstly, we consider u. U is equal to e raised to tan x Now observe this function e raised to tan x is simply a composite function. Therefore we can differentiate this u directly by using chain rule, or we can differentiate this y by using also logarithmic differentiation. Therefore differentiating with respect to x, du by dx is equal to derivative of e raised to tan x is e raised to tan x, and multiplying this derivative of tan x, d by dx of tan x is equal to e raised to tan x into derivative of tan x is sec square of x. This is by using chain rule. And suppose if we solve, or if we differentiate this y by using logarithmic differentiation, what will be the steps? Taking log on both sides, log u is equal to log of e raised to tan x, which is equal to tan x into log e, and we know that value of log is always 1. Therefore tan x into 1 is equal to tan x. Log u is equal to simply tan x. Now differentiate this log u. 1 by u. U is a function of x, therefore log u is a composite function. Therefore derivative of log u is 1 upon u into du by dx. 1 upon u into du by dx is equal to derivative of tan x is sec square of x. Therefore du by dx is equal to shifting of this shifting of this term of u into sec square of x, and u is equal to e raised to tan x. Therefore du by dx is equal to e raised to tan x into sec square of x. So by using both the methods, the answer will be the same. So consider this du by dx as equation number 2. Now consider v is equal to log x raised to tan x. Now by logarithmic differentiation, taking log on both sides, log v is equal to tan x is exponent here, tan x into directly log of log x. Now differentiating with respect to x, 1 by v into dv by dx is equal to u into v rule. Applying u into v rule, tan x into derivative of log x is 1 upon log x into d by dx of log x, plus log of log x as it is into d by dx of tan x, which is equal to tan x into here 1 upon log x into derivative of log x is 1 by x, plus log of log x into derivative of tan x is sec square x. Therefore dv by dx is equal to v into bracket, shifting of v into bracket, tan x divided by x into log x, plus log of log x into sec square of x, and replacing v is equal to log x raised to tan x, log x raised to tan x into bracket, totally tan x upon x into log x, plus log of log x into sec square x. This is equation number 3, and using equations 2 and 3 in equation 1. What is equation number 1? Equation number 1 is dy by dx is equal to du by dx plus dv by dx. Using equations 2 and 3, we can write the answer as dy by dx is equal to dv by dx is e raised to tan x into sec square x plus totally adding dv by dx log x raised to tan x into bracket tan x divided by x log x plus sec square x into log of log x. This is the final answer, and this question is to be asked for 3 or 4 marks for board exam. In this lecture we have seen examples on logarithmic differentiation. In next lecture we will study derivatives of implicit functions.